When two droplets meet, their fate seems sealed. Surface tension drives them to merge into one, and in the process, interfacial energy is released as heat and tiny fluid waves. This coalescence is irreversible. Once droplets fuse, they will not spontaneously separate back into their original forms. Thermodynamics dictates that energy flows downhill, disorder increases, and the arrow of time points forward. Doesn't it feel natural that merging is easy, while unmerging is forbidden? And yet, in carefully engineered microfluidic systems, droplets can be split with exquisite precision, as though the process were being rewound. By applying controlled flows, electric fields, or acoustic forces, a droplet can elongate, pinch at the waist, and divide into two nearly identical daughters. From a macroscopic perspective, the splitting can appear almost reversible. Droplets are divided and redivided with minimal loss, sometimes dozens of times in sequence. It seems to mock the inevitability of dissipation, as if soft matter could bend the arrow of time back on itself. Isn't it uncanny that irreversibility, so fundamental in nature, can be tricked into looking reversible under human control? The paradox lies in scale and precision. In natural coalescence, energy is released chaotically. Tiny vortices, waves, and heat scatter irretrievably into the environment. But in microfluidics, external control provides energy input and finely tuned conditions, channeling flows so that splitting follows predictable pathways. What looks like reversibility is really an exchange. Extra work is done by pumps, fields, or patterned geometries to counteract dissipation. The arrow of time is never truly reversed. It is disguised by carefully balancing losses with controlled inputs. Doesn't this reveal that irreversibility is not absolute but negotiable, depending on how cleverly energy is managed? A lesser-known fact is that researchers have observed near-reversible droplet operations in digital microfluidics, where manipulation costs approach the thermal noise limit. At that threshold, splitting and merging consume almost no more energy than molecular fluctuations already present in the liquid. Such experiments blur the line between irreversible thermodynamic processes and controlled, almost time-symmetric manipulations of matter. Could droplets, in this sense, serve as model systems for testing how reversibility emerges or fails at mesoscopic scales? The paradox, then, is that droplets are both the epitome of irreversibility and a stage for near-reversible control. Nature insists that merging dissipates energy, but human ingenuity finds ways to slice, split, and recombine with uncanny precision. Out of the same physical rules come both irreversible coalescence and apparently reversible division. The open question is whether this is simply a technological illusion or whether soft matter systems hint at a deeper flexibility in the arrow of time itself. Might microfluidic droplets be showing us that irreversibility, long considered absolute, is instead a spectrum where time's arrow bends but never quite breaks? Thermodynamics teaches that natural processes increase entropy, defining the arrow of time. Irreversible events such as mixing, diffusion, and coalescence transform ordered states into disordered ones. Droplet coalescence exemplifies this principle. As two droplets merging dissipate interfacial energy into heat and fluid motion, once merged, they cannot spontaneously separate back into the original droplet. This aligns with the second law of thermodynamics, anchoring irreversibility in everyday soft matter. The process consumes free energy stored in surface tension. Its outcome is stable and final. The arrow of time points firmly forward. Oil droplets in water merge irreversibly into larger drops during emulsification. It is like eggs breaking into a bowl. Once combined, they cannot unscramble themselves. In classical fluid mechanics, droplet coalescence is governed by surface tension forces. Merging reduces interfacial area, releasing stored energy into the surrounding fluid. This dissipation takes the form of viscous flows, capillary waves, and eventual thermalization. The energy cannot be recovered in a useful way, making the process irreversible. Molecular dynamics simulations confirm entropy always increases during coalescence. The merged droplet represents a lower energy, higher probability state. This matches the statistical inevitability of disorder. Coalescence embodies thermodynamic irreversibility at the mesoscale. Water droplets on a windshield merge into streams, never spontaneously splitting back into smaller droplets. It is like puzzle pieces snapping together, stable once combined, impossible to separate without extra work. Paradoxically, controlled droplet splitting in microfluidic channels can appear nearly reversible. In carefully designed flow geometries, a droplet elongates, necks, and divides into two nearly identical daughters. With precise control of shear, pressure, and surface tension, the process consumes minimal extra energy. The symmetry of the flow field allows splitting to mimic time-reversed coalescence. Unlike natural coalescence, dissipation is reduced to a near-negligible level. This engineered reversibility challenges thermodynamic intuition. It shows droplets can mimic reversible dynamics under constraint. In lab-on-a-chip devices, droplets are split repeatedly with negligible heating or loss of stability. It is like a magician cleanly cutting a rope in half and then rejoining it without fraying the ends. The difference between coalescence and splitting lies in energy control. Coalescence dissipates stored interfacial energy spontaneously, leaving no path for reversal. Splitting, however, injects just enough energy to overcome surface tension while preserving symmetry. Careful channel design and flow regulation minimize dissipation. This makes splitting a quasi-reversible process despite the same thermodynamic framework. The paradox is that irreversibility emerges from uncontrolled processes, while reversibility appears under precision control. Control becomes a substitute for entropy. Microfluidics turns disorder into order through geometry. T-junction micropanels allow repeatable droplet splitting with minimal variability in daughter size. It is like a trained gymnast balancing on a tightrope. What seems impossible is sustained by precise control. What seems impossible is sustained by precise control. At microscopic scales, the equations of motion for fluids are time-symmetric. In principle, reversing all velocities would reconstruct prior states. Yet in practice, dissipation and fluctuations enforce irreversibility. Microfluidics manipulates conditions to approach this microscopic symmetry. By constraining the system, effective reversibility is restored for short timescales. Droplet splitting thus highlights how time's arrow can be bent but not broken. It reminds us that irreversibility is statistical, not absolute. Controlled flows make rare reversals experimentally visible. High-speed imaging shows droplet neck thinning and pinching can be nearly symmetric in forward and reverse. It is like watching a film backward. The illusion looks real if carefully staged. Entropy explains why coalescence dominates naturally while splitting requires external input. Coalescence leads to fewer interfacial degrees of freedom, representing a highly probable state. Splitting, by contrast, increases interfacial area and requires lowering entropy locally. This is only possible by exporting entropy to the environment via precise control. In this sense, splitting does not truly reverse entropy but shifts disorder elsewhere. The paradox dissolves statistically, but the appearance of reversibility persists experimentally. Droplet dynamics embody thermodynamics in miniature. Entropy's dominance shapes outcomes. Unless control intervenes, microfluidic pumps and pressure gradients provide the entropy export needed for droplet splitting. It is like tidying a messy room. You increase order locally, but generate disorder in the trash pile. Harnessing quasi-reversible droplet dynamics enables transformative technologies. Microfluidic devices rely on precise droplet manipulation for diagnostics, synthesis, and single-cell studies. Near-reversible splitting minimizes energy loss, enhancing efficiency in high-throughput systems. It allows predictable, repeatable droplet cycles without destabilization. Applications range from biomedical assays to materials science. Reversibility becomes not just a curiosity but a practical asset. The paradox inspires new control methods across soft matter physics. Engineering thrives on bending entropy to human will. Digital PCR uses controlled droplet splitting to amplify DNA with high precision. It is like rewinding a clock to reuse its motion again and again. The paradox extends beyond microfluidics to soft matter and statistical mechanics. Other processes, such as vesicle budding, colloidal assembly, and granular rearrangements, show similar near-reversible control. These systems reveal how thermodynamic laws coexist with local reversibility. The lesson is that irreversibility is contextual, not absolute. With sufficient control, entropy production can be minimized, approaching microscopic symmetry. This reframes irreversibility as a spectrum rather than a binary. Soft matter thus challenges the universality of the arrow of time. It provides windows into controlled disorder. Vesicle trafficking in cells relies on energy-driven budding and fusion, resembling droplet splitting and coalescence. It is like turning a one-way street into a reversible lane with traffic signals. The thermodynamic irreversibility paradox is that droplets can both obey and defy the arrow of time. Coalescence is irreversible, dissipating energy and raising entropy, while controlled splitting appears nearly reversible. The same physics thus produces opposite outcomes depending on control. The paradox reflects the interplay of statistical inevitability and engineered precision. It reveals entropy's dominance, but also its negotiability at small scales. Soft matter systems embody the tension between law and exception. The arrow of time bends, but never fully breaks. This paradox exposes how reversibility can emerge within an irreversible world. A droplet merging with another cannot be undone spontaneously, but in microchannels, the reverse process can be staged with little loss. It is like seeing footprints in sand, irreversible under nature, but erasable when carefully smoothed.